In this video, we're going to talk about collisions and how collisions relate to momentum and its conservation. And we're going to keep this very simple. We're going to really just talk about two main types of collisions. There's probably, you could break those down in some other subcategories, but for what we need to know, we're going to kind of keep that as two. But before we do anything with collisions at all, we want to make sure we kind of make one big statement here. And then that is that momentum is conserved in all situations, which basically kind of comes down to this formula idea that the total momentum that you start with has to equal the total momentum that you finish with. And we'll work with this formula and with some conservation momentum examples later. It's really not a formula. It's just saying the total momentum you start with has to equal your momentum that you end with. But before we say too much about collisions, I just want to make sure we understand momentum is always conserved, period. There is no situation where momentum would not be conserved. And that kind of leads us into the two different types of collisions that we have to be aware of. And what these kind of do is they'll pop up and they'll say two objects collide elastically. And they don't really say it's an elastic collision, but they let you know then that because it's an elastic collision, because they collided elastically, that you're going to have something be conserved. And that's how we define these collisions. So the two different types, there's, we'll just go one. There's something called elastic collisions. And I guess one bullet here, P is conserved. I guess we're really overemphasizing this, but we don't want to forget that. The other thing is what we call mechanical energy. Is conserved. That's your kinetic and potential types of energy. And that obviously was kind of defined in an earlier video, but those are the two types of energy that you have to sometimes check for with these collisions. Just kind of switching over. The other types of collisions are what we call inelastic. And again, momentum is conserved, but mechanical energy, ME, is not conserved. So to give you some examples of these things, let's see. The most common are atomic collisions. This would be like a proton strikes another proton, and the two things then rebound off each other, or atoms or molecules colliding. Honestly, it's a pretty small amount of the collisions that we will be working with. Another example is sometimes billiard balls. Oops, let me try. I gotta fix that. That's brutal. But if we don't ignore some aspects of the sound that a ball makes when it strikes another ball and stuff like that, it really is not conserved. So that's why I put a question mark after this, because sometimes they'll see two billiard balls collide elastically, or two billiard balls collide and ignore the effects of sound and friction, and then they would become elastic collisions. So they have a high, they're probably the closest thing that we have that has an elastic collision other than atomic collisions. But sometimes the numbers here are hard to work with because they're very, very small. And sometimes the speeds are very, very high, and it's just easier sometimes to work with something like a pool ball because people can visualize that. And our examples for inelastic collisions is basically everything else. So basically that's just saying that most things that have collisions will have an inelastic collision, but not everything, and that's not always guaranteed that way. So what we want to do is kind of go from these ideas now into some examples. And here we just have two balls. We don't really know what they are. They could be atoms, they could be billiard balls, they could be two kickballs like from the playground. And they're basically being rolled towards each other. And you can see we have before and after. Now, as you've seen with the momentum problems that we did earlier, it's always good to draw pictures to kind of help you sort your information out the best that you can. And in this case, we have a ball rolling to the right with 2.5 meters per second. It has 160 gram or 0.16 kilogram mass, and another ball is rolling left at -1 meters per second. We defined left now as being negative and has a mass of 0.22. So afterwards, this ball rebounds and rolls backwards, and then this ball, we don't know what's happening with this. It could be going right or left, depending on how much momentum we had here. And that's kind of what the formula, the conservation momentum formula, does for us. So we're going to start with that, which is going to be the total momentum initially is going to equal the total momentum at the end. Now, I'm going to say the momentum of the blue ball, PB, I'm going to put I plus PRI is equal to PBF plus P, or momentum, RF. Now we have to be careful. You get all these subscripts kind of going and it gets really confusing. Understand that just helps us understand what numbers are going to go into this. These still really just break down to an MV plus an MV equals MV plus MV. And I guess I'm okay with just putting MVs because we can check right here before to see that this is for the initial blue and the initial red and so on. So what we have to do is start putting our numbers in here. So I have 0.160. I'm going to do kind of a no-no. I'm not going to label things as I'm going through because I don't want it to get too confusing. But it's not a bad idea to do that. Just in my little tablet here, sometimes it works a little bit better if you don't, as far as keeping things organized. So we have 0.16 times 2.5 plus 0.220 times -1. I'm going to do something here. I'm going to change this speed. I know it's not the nicest thing to do in the middle of the problem, but I'm going to make that -2 meters per second because that's how my examples worked out over here. So that really doesn't change a whole lot yet. It would make a difference later on, definitely. But sorry about doing that to you. -2 is equal to 0.160. Now we know this speed is -1.25. I didn't put the negative up here, but you can see that it's moving in the opposite direction, so maybe a little negative sign would be a good thing there. Plus 0.22 kilograms times velocity. So as we start working through here, we can see that this is going to come out to be 0.4 minus 0.44 is equal to -0.2 plus 0.22 times V. Now again, I'm being kind of lazy by not labeling all that stuff, but now that we combine our like terms, we're going to get -0.04 is equal to -0.2 plus 0.22. If I add 0.2 to each side, I end up with 0.16 is equal to 0.22, so this is 0.22 V. And then I just solve for my velocity, and I get 0.73 meters per second going to the right. Or a positive velocity just kind of indicates that this is moving to the right. So I can now kind of sketch this in here that the velocity is equal to 0.73 meters per second going this way. So that answers the first part of our question. The other question here that we didn't necessarily write out is this an elastic collision or an inelastic collision? And this doesn't tell us. We know this momentum was conserved, but after that we're not really sure. So what I'm going to do is I'm going to get rid of this because we have our information from it. Let me clean that up. And right now we have to look at if I'm going to have a conserved mechanical energy. If mechanical energy here is conserved, then I know that my collision was elastic. So the initial mechanical energy has to equal the final mechanical energy. So I just did M for mechanical energy here. It's supposed to be I. I didn't dot it very well for some reason. What type of energy are we dealing with this? Well, it's not moving up or down, so it can't be potential. It's only moving right and left, so that makes it kinetic energy. So it's kind of like kinetic energy for the blue initially plus the kinetic energy for the red initially must equal the kinetic energy for the blue final plus kinetic energy for the red final. If this is equal, it's an elastic collision. If it's not equal, if this side doesn't equal this side, then it turns out to be inelastic. So again, this is going to be 1/2 mv squared plus 1/2 mv squared is equal to 1/2 mv squared plus 1/2 mv squared. So 1/2 times 0.16 times our velocity squared, 2.5 squared, plus 1/2 times 0.22 times our velocity here, which is -2 squared. Negative, positive doesn't matter. That's going to become positive. Is equal to 1/2 times 0.16 times 1.25 squared plus, make this 1/2. I'm running out of room here. 0.22 times of speed here, which is 0.73. Squared. Now you can kind of look. You can see we have bigger velocities on this side. Those become positive, so this number gets much bigger than what this side will be. And we end up getting 0.94 joules on this side, and I'm going to assume that you can do this and add it together, is equal to 0.184 joules. And you can see, no, they're not equal at all, which tells us this is an inelastic collision. So that's all the time we have for this problem. The reason this is inelastic is because our energy was not conserved. If this side and this side were both equal, if this would have somehow became 0.94 joules, then you would say it was an elastic collision. And that's kind of where these collision ideas pop up. So that concludes our collisions.